So today we're going to finish off, I think mostly finish off chapter 3 on a series. And there's a couple of topics just to say a little bit about. The first of these is what we've called a telescopic series. So the name will become apparent when I'm referring to here shortly. We'll have a look at an example here. Can we find the value of the series? The example we're going to take at the start is sum from n equals 1 to infinity, 1 over n times n plus 1. Okay. When you look at this, okay, first of all, you have to worry whether this is convergent or divergent. But when you look at the term, see the term is 1 over n squared plus n. So the dominant feature of that term is having an n squared in the denominator. So if you apply the standard comparison test to that and you compare it to the term 1 over n squared, you find it does compare to that, and because the sum of 1 over n squared is convergent, that will say that this is convergent as well. Okay. So applying the comparison test, either the comparison test or the limit comparison test, comparing with the sum of 1 over n squared, which is we know to be convergent. We know this is convergent also. This series, we know it's convergent, approximately like the sum of 1 over n squared. But can we figure out the actual value of the series? And for some series like this, there is a technique. That you can use. And the technique is we can make use of so-called partial fraction expansions. Partial fraction expansions. So I'll just say now we're going to be looking at these in detail in a later chapter, in chapter 3 on functions. But I'll just say, give you a little bit of info about what they are here. For a rational function R of n, I'll tell you what a rational function is now. A rational function R of n, i.e. it's a quotient or a quotient of polynomials. Okay. So P and Q are to be two polynomials in the variable n, and our function R of n then is just P of n divided by Q of n. This is what we call a rational function. Quotient of polynomials. Do ask me if anything's unclear in my handwriting. Yeah.
When it says partial fractions, what's the word?
Expansions. Yeah, partial fractions. Expansions. If the degree of P is strictly less than the degree of Q, okay, so remember, polynomials have a degree, which is the highest power of n that you see in the polynomial. So this is the case for our series. Because the numerator polynomial P is just a constant 1, that is degree 0, whereas the denominator polynomial, which is n squared plus n, that has degree 2. If the degree of P is strictly less than the degree of Q, then we can expand R of n into a sum of simpler rational functions. Now, it's a sum of a lot of terms, okay? Adding up a lot of terms. Each of the terms will be a simpler rational function than R itself. There's a couple of rules that we use for every factor that has the form n plus a to the power m of the polynomial q. We have terms, well, there'll be something over n plus a plus something over n plus a squared okay, so if there's a factor, when you factorize the polynomial q, if you see a factor in it which is n plus a to the power m, that's going to generate n terms like this in your partial fraction expansion. Where the alpha I here, these alphas are real constants. Now your polynomial might also have factors, they might also have quadratic factors. We'll explain about this more in chapter 3, but there's a result that says that any polynomial can be factorized, any polynomial with real coefficients can be factorized into factors like this, linear factors and quadratic factors. Okay. You can always break the polynomial with real coefficients down into a product of polynomials like this. But if there are any of these in our rational function, I think the examples we'll look at today will be simple enough, so there won't be any of these. But for these ones, we get terms, we have terms beta 1 over n squared plus an plus b, and again beta 2, and this time you'll have that factor read squared, and then all the way up as far as beta n squared plus an plus b power n. So each of those two types of factors in the polynomial q generates terms like that in the partial fraction expansion. Again, the bi, these coefficients bi are just real numbers, they're not polynomials or anything. The numerators, alpha I, beta I that we see here are determined by comparison with R. And we'll show you an example of this. Okay. So that's just a really quick basic information about partial fraction expansions, about the simplest kind. That there. Oh, excuse me. Sorry. Sorry. These numerators are Bn plus a gamma. Sorry. These numerators are order 1 polynomials in this case. Gamma I, beta I are real numbers. Sorry, the numerator, when you've got one of those irreducible quadratic factors, n squared plus an plus b, then the numerators have to be order 1 polynomials. Okay, let's see an example of that in our case here. Okay, so the rational function we're looking at is this rational function 1 over n times n plus 1. So the PFE, the partial fraction expansion of Rn, which is 1 over n times n plus 1, this is going to be Rn equals 1 over n times n plus 1. This is going to be some constant over n plus another constant over n plus 1. Okay? Because our numerator here has 2 factors in it. There are 2 linear factors of the form n plus a raised to some power n. So a in the first case is 0, and a in the second case is 1. And the n, the exponent in both cases, is just 1. Okay, because you just see the factor n, power 1, and the factor n plus 1. So it should be possible, if you're to believe me on this, it should be possible by the technique of partial fraction expansions to write 1 over n times n plus 1 as something over n plus something over n plus 1. And we can figure out what the alpha and beta are. So at the moment, I don't know what the alpha and beta are. But if I add the fractions together again, if I force them together again, see what happens to the alpha and beta. Well, when I add these together, the alpha will have to be multiplied by n plus 1, and the beta will have to be multiplied by n. Okay, that's just the rule for adding symbolic fractions. Okay, you put them over a common denominator. Here, the common denominator is n times n plus 1. So we have alpha times n plus 1 plus beta times n. And then you can reorganize the numerator into a standard form as a polynomial in n. And you see it has that form there, alpha plus beta times n plus alpha. And when I said that these constants, these unknown constants that appear in the partial fraction expansion, we determine those by comparison with the original rational function. So you see here, the two numerators are the same. We've got these two fractions equal to each other. Both of the numerators are the same. So it has to be the case that both of the denominators are the same, parts of the bottom of the fraction. So both of the numerators have to be the same. So this implies that the numerator 1 on the left up there must equal alpha plus beta times n plus alpha. And if we're saying that these two are equal, these are two polynomials in n. On the left-hand side, we just have a constant. On the right-hand side, we've got what looks like an order 1 polynomial. Two polynomials are equal. Then corresponding coefficients of powers of n must be. Okay, that's a principle about polynomials. Two polynomial functions can be the same only if corresponding coefficients are the same. So the constant coefficient on both sides, the constant coefficient is 1 on the left-hand side, and it's alpha on the right-hand side. So alpha must be 1. And also, the coefficient of n must be the same on both sides. Now, the coefficient of n on the right-hand side is alpha plus beta. What's the coefficient of n on the left-hand side? Well, we don't see an n on the left-hand side. There isn't one written down. So that means its coefficient is 0. What's multiplying n in this polynomial on the left-hand side with 0? So we don't see it. It's alpha plus beta. And those things together give us our solution. Alpha must be 1 and beta must be minus 1. So in general, when you form the partial fraction expansion and put the thing back together as a single fraction again, you then have a complicated numerator here, which you compare to the previous one. In general, what you have here is a system of linear equations. System of linear equations in the unknown parameters or coefficients of the partial fraction expansion. And you've been learning in your linear algebra, you've been learning about solving systems of equations using Gaussian elimination, row reduction. Yeah. So that's an example of, that's a kind of an example where that kind of class of problems naturally arises, where you naturally see systems of linear equations coming out. Now, if you've just got two equations and two unknowns, you don't have to laboriously apply the formal algorithm of Gaussian elimination. You can normally just solve it quickly by substitution. But in general, if it was a complicated example, you may have many equations here in the unknown constants, but in principle, you can solve it using the Gaussian elimination, or you can type in the system of equations into MATLAB and ask it to solve it, and it'll tell you the solution. So where are we then? So that means we can say the sum of our series, this is the question I posed at the beginning. By a comparison test, we know this series is convergent. Can we actually figure out what the value of it is? To what limit is this infinite series converging? Which, as it stands there, is a kind of hard problem. It's hard to evaluate just a random infinite series. It's hard to say exactly what the limit is. You can approximate it by looking at how the series is evolving. To get a precise description of the limit can be difficult. But in this case, you're going to see it suddenly becomes a lot easier. So if we use the partial fraction expansion here, so we've got 1 over n minus 1 over n plus 1. It suddenly becomes a bit easier because, by definition, this is equal to the limit of the partial sums agreed? That's the definition of the sum of an infinite series. It's the limit as k goes to infinity of the kth partial sum. There's the kth partial sum there, just adding up the first k terms. Now, because we've got a plus 1 over n and a minus 1 over n plus 1, when we look at all the terms that there are in this partial sum, most of them cancel off. Because when n equals 4, I see a plus a quarter here, 1 over 4. But when n was 3, I saw a minus 1 over 3 plus 1. I saw a minus a quarter. So that plus a quarter and minus a quarter will cancel out the effect of each other. And that happens for almost all the terms of the partial sum. A positive term, 1 over n, gets cancelled by an earlier negative term, 1 over n plus 1, when n had a value 1 lower than it had afterwards. So later positive terms get cancelled by earlier negative terms. So that means most things cancel, but there's some things left. There'll be some things left at the front, which will be the early positive terms which don't have. Will be the positive terms at the front that don't have an earlier negative one. And there'll be some negative ones left at the end, for which the cancelling positive bit hasn't come yet. But you can see what's going to happen if you expand out your partial sum there. So the first term is when n is 1, so you get 1 minus a half. The next term is when n equals 2, so then you get plus a half minus a third. Then it's when n equals 3, you get plus a third minus a quarter. And you're going to keep going in that pattern. Let's write in the last two terms. The second last term is when n is equal to k minus 1. Then you've got 1 over k minus 1 minus 1 over k. And then the very last term is when n is equal to k. So you have plus 1 over k minus 1 over k plus 1. So as you can see, most of those terms there aren't going to survive, okay? Because most of them, minus a half cancels with plus a half, minus a third cancels with plus a third, minus a quarter will cancel with plus a quarter, which comes straight after it, and so on and so on. This this minus 1 over k cancels with a plus 1 over k. This minus 1 over k plus 1 over k minus 1 cancels with a minus 1 over k minus 1 which came before it. So the only things that don't cancel are the first term and the very last. So the positive terms normally cancel with something that came before it. Because nothing comes before the 1 because that's the first term. And the negative terms you see normally cancel with something that comes immediately afterwards. So this last negative 1 doesn't cancel because there's nothing after. So this greatly simplifies the partial sum. Agreed? Our k partial sum is now no longer a sum of k different things. It's now just a sum of two things. This constant 1 and this term minus 1 over k. And can we take the limit of that quantity? Well, yeah, we can use our algebra of limits theorem for sequences. Here we're taking the limit of a constant minus this term 1 over k plus 1. So as k gets larger and larger, that term minus 1 over k plus 1 is going to get smaller, smaller, smaller to converge to 0. So this limit is simply 1. And that's by the algebra of limits. So we've got this 1, and this started off being the sum of the infinite series. So we have it. Okay, the sum of the infinite series here is equal to 1. So we've been able to evaluate the infinite series. So we've shown that when we add up all these terms 1 over n times n plus 1, we get exactly 1. Okay. Using this tool of a partial fraction expansion. Okay. So if you know that if you're looking at an infinite series where the term is a rational function of the index variable, polynomial in the index variable divided by another polynomial in the index variable, then using a partial fraction expansion of the rational function can allow you to draw conclusions about the sum of the infinite series. So we could have another look at another example. Or first of all, any questions about that one? Anything about it that you'd like me to clarify or say something about it again? Note there where we've used the definition of the infinite series. That there is true because that's just the definition of an infinite sum. The infinite sum, the sum from n equals 1 to infinity of this thing is just the limit of the sequence of partial sums. That's the definition we gave to the infinite series. But then when you're just looking at a finite sum, you can expand it out, spot some cancellation patterns that are happening there, and determine what it is. Okay, so let's look at another example of one of these. And I'm taking this from the 2014 summer exam. You can see these past summer exams. They're linked to from the Moodle page. If you look at the library block on the right-hand side of the Moodle page, you'll see links to a number of past exams. And one of the parts of one of the questions there was evaluate the sum of the series or the value of the series, sum from n equals 1 to infinity of 2 over m squared plus 3n. Okay, it's a similar looking problem to the previous one. We're summing a rational function on the index variable. Again, it's not too complicated. It's constant over a quadratic polynomial. So we'll seek the partial fraction expansion of this. So my 2 over m squared plus 3m. Of course, you can see how the denominator factorizes into m plus 3. So by those rules for the partial fraction expansion, what we expect to see is two terms, something over m plus something over m plus 3. We don't know what those constants are to begin with, so we can determine what they are. We collapse the thing together again as a single fraction, and you'll see an alpha plus beta multiplying m plus a 3 alpha. Okay, so this final version of the fraction, we compare to the first one, where we saw 2 over m squared plus 3m. They both have the same denominator, so they can only be equal if their numerators are equal. And their numerators are two polynomials in n, got a constant polynomial there, and this order 1 polynomial in m, something times m plus another constant. And those two can only be the same if the corresponding coefficients are equal. So the constant coefficient here must equal the constant coefficient on the right-hand side. Constant coefficient being the one that isn't multiplying m, just sitting there as the constant in the polynomial. And the m coefficient on the left-hand side, which is 0, so there isn't an m there, that must equal alpha plus beta. So we have a system of linear equations, 2 equations and 2 unknowns, so it can certainly be solved using Gaussian elimination, but it's telling you what it is straight away there. So the alpha must be 2/3, and the beta must be -2. Okay. So we can apply this now to the series. So our series can be expressed as, well, let's write it down originally, 2 over m squared plus 3m. This is, bringing the partial fraction expansion, is 2/3 over n minus 2/3 over n plus 3. And now we can run the same argument as before. By definition, this is the limit of the sequence of partial sums. Okay, the limit of that sequence of partial sums. Now, this now is just a finite sum we're looking at, plain old summation from m equals 1 up to k, those values. So that 2/3 there, we can factor out that 2/3 and bring that all the way out to the front. So we can write this as 2/3 times the limit as k goes to infinity. And now we'll start writing it, well, no, let's just write this down. Just complete factorization. So it's 1 over n minus 1 over n plus 3. So taking the 2/3 out of the way simplifies, means we don't have to deal with the fraction all over the place. Just factor it out to the front. So what we're looking at is 2/3. And again, because one of these is positive and the other closely related one is negative, you're going to get a lot of cancellation. But what's happened here is the denominators are m and m plus 3. So the cancelling pairs are a bit further apart. So that means there's going to be more terms that survive. So, I mean, you can do it all in your head and figure out what's happening, but to make sure you don't miss anything or miscount things, it's probably a good idea to look at the beginning of the partial sum, spot the pattern of what's happening, and then look at the end, so you can see what's remaining at either end. Okay? The things that don't cancel are going to be at the front and at the end of the partial sum. Everything in the middle of the partial sum, once you spot the pattern, the behavior of what's happening, those terms should all cancel. So how's this partial sum looking? Well, when m is 1, it's 1 minus a quarter. When m is 2, it's a half minus a fifth. When m is 3, it's a third minus a sixth. Still haven't seen any cancellation yet. When m is 4, it's 1/4 minus 1/7. Okay, I'm starting to see cancellation. Minus a quarter is cancelling with plus a quarter. Let's just go one more. When m is 5, it's going to be 1/5 minus 1/8. Okay, you can see I've got another cancellation there with minus 5 and plus 1/5. Minus 1/5 and plus 1/5. Okay, that should be enough to spot the pattern of what's happening. Now let's go for the last few terms. How many terms did I have to get to see? So let's go 1, 2, 3, 4. I have to put 4 terms at the start to see the cancellation. So maybe I should do the last 4 terms. So the fourth last one is when m is k minus 3. So it's 1 over k minus 3 plus 1 over k. Sorry, minus 1 over k. So that's when m is equal to k minus 3. So the m is k minus 3, the m plus 3 is k. Then the next term after that is 1 over k minus 2 minus 1 over k plus 1. And then you plus 1 over k minus 1 minus 1 over k plus 2. And then finally, you plus 1 over k minus 1 over k plus 3. Okay, so that's the front and the end of the sequence. The reason I've had to put a lot of terms down there is the cancelling pairs are a little bit further apart. They're 3 steps apart. But we can spot the pattern now of what's happening. Okay, the 1 doesn't cancel with anything, but this minus a quarter cancels with that plus a quarter. That minus a fifth cancels with the plus 1/5. The next negative term, minus a sixth, that will cancel with this plus a sixth, which is coming next. The next term, when n equals 6, you'll get a plus 1 over 6. So what you're seeing there is that negative terms cancel with a positive term that comes 3 steps later. The negative term cancels with the positive term that comes 3 steps later. So this positive term, sorry, the negative terms cancel with positive terms. Yeah, so this positive term will cancel with an earlier negative one. So will that one there. So will this one there. So will that plus 1 over k. You can see the one that cancels with it there, minus 1 over k. Okay, so everything cancels. It's a little bit more complicated to see than the previous example. Everything cancels except for the 3 positive terms at the front, right? Because they don't have an earlier negative term because they're at the front. The things that would cancel them would come here, but there are no terms there because this is where the thing starts. And also these 3 negative terms, we'd expect them to cancel with positive things that come later. But there are none because this is the end of the partial sum. So they don't have cancelling partners. So let's just write that out. So we can omit all the cancelled stuff. We've got 1 plus a half plus a third minus 1 over k plus 1 minus 1 over k plus 2 minus 1 over k plus 3. Okay, that has simplified the partial sum. Because whatever the value of k is, if k was 100, with some of the first 100 terms of the sequence, all we've got left are these 6 terms. We'll only ever have 6 terms left. There's 3 constants at the front, so they don't change. And these 3 terms here, though these 3 terms are getting smaller and smaller, and they're converging to 0. When you take the limit of this sequence by the algebra of limits theorem, this is just equal to this, because those terms go to 0. And that is whatever it is. What's that? It's a little 6. 6 plus 3 plus 2. It's what? 11 sixths. 11 sixths, 22 eighteenths. So 2 goes there, 3. So 11 ninths. 11 ninths seems to be the value. That's it. So it's really nice. Not only have we discovered, we would have known that the series, you just see the series there at the top of the page. We would have known that the series is convergent by doing a comparison test with the sum of 1 over n squared. Okay, because that's the dominant structure there is 1 over n squared. As n gets larger and larger, it's the fact that an n squared in the denominator, which is the dominating feature of that. So a comparison test would show us that that does converge. But using this analysis, using the partial fraction expansion of the term, you can spot that you get this nice cancellation of partial sum, so that the evaluating the limit of the series just comes down to evaluating some terms at the front of the series. Okay? Everything else is cancelled out in the evolution of the infinite series. Okay? So you can see why we use the term telescoping. So this is sometimes called the telescoping of the partial sums. You know, those like kind of cartoon version of a telescope you might have on the ship. When you're using it, extend it out like that, but to put it away, it all kind of folds up. Collapse the thing and folds up on itself. So this behavior from having a very long partial sum, when you write it out first, but then you spot this cancelling behavior that's going on in the middle, so it mostly shrinks down until you got a bit of the front of the bit at the end, which is still surviving. And the bit at the end is shrinking to 0, it's converging to 0, so it's just a bit of the front that survives. Okay. So there's a question or two like that, or I think just maybe one in the end of chapter exercises. There's a good few more on the tutorial sheet. So when you look at the tutorial sheet on the series, it's got a number of examples of this for you to try. So it can be a bit of a lengthy process if the rational function that you're summing is complicated. We've got a lot of factors. There might be a lot of stuff to determine there. But it is one of these, it's one of the few kind of cases where you can arrive and you can precisely quantify the sum of the infinite series, which in general is quite hard to do. Okay. So it's a nice example of that. Okay, so as I said, for the tutorial, have a look at those questions. The last few questions on the tutorial sheet. And then when I see you next week, okay, there is this topic of power series, which is in that chapter, but really the proper place for that is when we're considering differentiation. So we'll talk a bit about power series and how we apply some of these convergence series ideas to that when we meet the derivative. Okay, in a few chapters time. Okay, I'll leave it there this afternoon.